Hi, welcome to your Unit 2 Lesson 8 notes, which is all about inverse functions. In this video, we're going to work through all 10 examples, just chatting about what inverse functions are and what that means by finding them algebraically, how to verify them using compositions. So let's begin. So we know that a relation is a set of ordered pairs. A function is a relation in which for each distinct value, there's exactly one corresponding y value. If a function f is a set of ordered pairs x, y, then the f of f is a set of ordered pairs y, comma, x. Remember, finding inverses, we flip-flop the x and the y's. When the inverse of the function f is itself a function, then we can say that that f original function is considered one-to-one. So if you look down at example 1, we have our mapping diagrams of our relations. This one is a function because 1's only mapped to 4, 2's mapped to 5, 3's mapped to 6. And if we go backwards, the opposite direction, 4's only paired with 1, 5's only paired with 2, 6 is only paired with 3, which makes it a one-to-one function. The middle one is a function because 1's only paired with 4, 2's only paired with 4, 3's only paired with 6. So it is a function, but it's not one-to-one because it's inverse. 4 is paired with 1, 4 is paired to 2. So right there, that would make it not a one-to-one function. And the third one there in example 1 is not a function because 1 is paired with both 4 and 5, so that's what makes that not a function. If a graph of a function is known, you can use the horizontal line test to determine whether the function is one-to-one. So if every horizontal line intersects the graph of a function f and at most one point, then we know that the function is one-to-one. So if we have our original function here, which is listed in black, if I do all of my horizontal lines passing through it, it's not going to intersect it more than once. So I know then that the inverse itself would be a function. The graph of the functions are always going to be reflections over the line y equals x, which is your identity function, which is highlighted here in red. If you are given a function, our notation in function notation for the inverse, remember, is that f with the -1 looks like an exponent, but it's not an exponent. If we're not in function notation, we can just do y with that -1 superscript. The domain of a function will be equal to the range of the inverse function, and the range of the function is going to be equal to your domains, because remember, with inverses, you're just flipping the x and the y, so they would be inverses of each other. So if you look over here on this graph, on our original function, we had an ordered pair. This one looks kind of nice at 1, 3. So if I flip my x and my y's, that means 3, 1 should lie on the inverse, which it does. Okay, moving on to example. Okay, moving on to example 2. So it says for each of the graphs below, we're going to draw the line y equals x, sketch the inverse of the function on the same grid, and then decide if the function is one-to-one or not. Okay, so my identity line starts at 0, up 1 over 1. I'm just going to make it with dots because these rectangular grids throw me off a little bit. Okay, so there's our identity line, y is equal to x. So if this is function f of x, I'm going to do it in a different color. I'm going to do it in blue. The inverse should be all these points kind of flipped, right? So this point right here is at, looks like -3, -2. So if I did the inverse of that, then that would put me at -2, -3 down here. Put it in purple. Where's another nice point on our original function? Looks like -2, 1. So -2, 1 would, -2, -1 would flip to -1, -2. My next nice point looks like it's right here at 1, 0. So flipping 1, 0 to 0, 1 would be my next point on my inverse. Let's get another one. How about 6, 1? That looks pretty nice. So the inverse of 6, 1 would be 1, 6, which is up here. So I would have my graph kind of looking like that for my inverse. So let's call that F inverse of X. So is our original function 1 to 1? I would say yes. F is 1 to 1. It passes the horizontal line test. I can't make a horizontal line go through it more than once. Plus, we were able to find the actual inverse itself, right? So the function itself does exist for its inverse. Okay, part B. Let's go ahead and dot in our identity line. Kind of like that. Okay, so now let's go ahead and pick out some points and relocate them. So -2, 0, -2 would relocate to -2, 0. What else do we got? We've got 2, 2 would relocate to 2, 2. -2, 2 would relocate to -2, like this. So we kind of have this happening as our function itself. So here is F inverse of X, which is not a function, right? My vertical line test, remember we use vertical line test to determine if something is a function or not. It doesn't pass the vertical line test. My original function did not pass the horizontal line test because it's crossing twice. So we will say F of X is not 1 to 1. The inverse is not a function. Or we could just say simply it doesn't pass the horizontal line test. Okay, so definition of our inverses. If we have two functions, let's say f and g, and we want to determine whether they are functions or not, if we do a composition of the two functions, my output should be x. And if I do a composition in reverse, my output should also be x. So we can use this test to verify. So the function g is the inverse of a function f. It's denoted by our notation. So if I do a composition between the two, I should have an output of x, right? And remember that your domain of f will be equal to the range of your inverse. So if I wanted to test, for example, 3, whether f and g were inverses of each other, I'm going to do an f of g of x. So let's go ahead and do that. So I'm going to plug in my g function into my f. So 4 times x minus 3 over 4 plus 3. These 4's cancel, so x minus 3 plus 3 gets us to x. That checks. Do it the other way. Make sure that also gets us an x. So now I'm going to do the reverse. I'm going to plug my f function into my g. So 4x plus 3 minus 3 all over 4 gets me 4x over 4, which is just going to get us x, which checks. So we verified that they are functions of each other, so therefore, because f of g of x is equal to g of f of x, which is all equal to x, we can show that they are functions of each other. All right, so now let's actually find some inverses. So given a formula for a function f, we are going to find an inverse by determining that an inverse 1 exists. And by doing that, we're going to check to see if it's 1 to 1. So we could ask ourselves, is it necessary to restrict the domain to get a 1 to 1 function on f? If it's not, then we can interchange the x and the y's, solve for y, find our inverse, state any restrictions on our domain on the inverse, and then just make sure your y gets replaced to inverse notation. So example 4. We have the following function. It's a square root function. Let's go ahead and sketch it. So we have a shift to the left 3, down 2 for my vertex. Left 3, down 2 tells me that my starting point of my Square root is going to be there. I don't have a vertical stretch or compression happening, which means if I go 1 unit to the right, it should just be up 1, which let's confirm that. -2 plus 3 is 1. The square root of 1 is 1. 1 minus 2 is -1. Good. Let's pick another value to put in. What's another nice number to take the square root of? 4. So that would mean x would have to be 1. So if I plug in 1 for x, I get 4. Square root of 4 is 2. Minus 2 is 0. So we're getting a function that looks kind of like this. So let's label that f of x. Okay, the domain of that function is from -2 to infinity. The range of that function is, -3. I was zoomed out or in too much, I didn't even see it. So -3 to infinity. My range, I actually looked at my screen here, is -2 and higher. Okay, so now let's find the inverse. So I'm going to make my f of x, which really technically is a y, an x. I'm going to make my x a y. And we're going to solve this for y. So I'm going to add that 2 over. So x plus 2 equals the square root of y plus 3. Squaring both sides gets me x plus 2 squared equals y plus 3. Subtract your 3 over. X plus 2 squared minus 3 is equal to y. And now I'm just going to rewrite my answer in function inverse notation. So f inverse of x is equal to x plus 2 squared minus 3. And my domain for that is going to be the range, which is -2 to infinity. And the reason why we need to restrict it is this right here is a parabola, right? And a parabola does not pass the horizontal line test, right? That's a parabola shifted to the left 2, down 3. So it's kind of looking like this. Don't put this on your paper, just watch for a second. Doesn't pass the, well, 1, it's not the whole entire inverse of this, right? This is just one side of our whole entire function. So what side of our function do we need it to reflect to? We just need the right side of this graph, right? Let me get rid of that. So we're just going to go from here up, right, for our function. Actually, I think it's a little bit steeper, but we get the idea. So here is your inverse, right? So I want to restrict it to the domain, which is the same as my range to the original function. So it's always good to think about your domain and your range of the original, because your range of your original will be the domain restriction that you use for the inverse. Okay, let's do it for number 4b. Here we have g of x, which is cubic, or cube root. So we're shifted to the left 2, down 1. It's going to be something that looks kind of like this, but let's get some points. There's no compression or stretching, so it's just going to kind of look like this. Can we get something on the right? What's a nice cubic number besides? So 1. What comes next? 8. So 6. If I plug in 6, so we're already off the chart. If I plug in 6, I get 6 plus 2, which is 8. Cube root of 8 is 2. 2 minus 1 is 1. So like, I don't know, it's going to be somewhere out here, so it's kind of flat. So flattens out a little bit. There we go. Okay, so my domain has no restrictions, so all real numbers. My range has no restrictions. Even though it's flattening out, it eventually will get to all points on your y-axis. Okay, so let's find the inverse. So I'm going to make that g of x and x. I'm going to make my x a y. Sorry about that. Solve for y, add your 1 over, equals the cube root of y plus 2. Take everything to the third power, so then we have x plus 1 to the third power equals y plus 2. Subtract your 2, x plus 1 to the third power minus 2 is equal to y. Put it in inverse notation, I think we're in g, so g inverse of x is equal to x plus 1 cubed minus 2. Which your domain for that is going to be the range of the original, which was all real numbers, so I don't have any restrictions happening for that, right? So when I go to graph it, Negative 2, 0 would go to 0, negative 2. Negative 1, 0 would go to, oh no, hold on, I didn't do that right. Negative 2, negative 1 would go to negative 1, negative 2. I'm trying to go speedy here. Lunch is right around the corner. Negative 1, 0 would go to 0, negative 1. Negative 3, negative 2 would go to, did I already do that one? Negative 2, negative 3. There we go. So it's going to look something like this. Where, I guess, 1, 6. So maybe a little bit steeper. Okay, moving on. Okay, so now the second part of these notes is now going to take these inverse function concepts and apply them into real-ish life scenarios. So let's let C of M be the cost in dollars of M ounces of mangoes. What do the following statements tell you? Be sure to use units. So if I'm doing C of 12 is equal to 0.75, that 12 represents my M, which is my mangoes. So 12 ounces of mangoes costs 75 cents. Which means over here, 8 ounces of mango costs 50 cents. So now when we do the inverse, this now is representing technically my Y, which my Y was your cost. And now this is your M, which was mangoes. So it tells us that it's going to be $3 will buy 48 ounces of mangoes. This one, 75 cents, will buy 12 ounces of mangoes. Okay, so in example 6, we're just going to take that a little bit further. So we have W is equal to P of X is the average daily quantity of water in gallons required by a palm tree of height X feet. So if P of X, so X, this is your X, which is in feet, right? So P of 25 would represent the average daily water needed for a 25-foot palm tree. Oops, it's spelled palm tree. If we do the inverse, right, so this now becomes still our water, right? So now this is our W is going to be equal to our X. So the height of a palm tree, right, because this is going to be equal to whatever X is, and our X represents the height of a palm tree. So the height of a palm tree that requires 25 gallons of water. Okay, so for C, what does the equation P of V equals 50 tell us? So remember this, V is the same as kind of our X, right? And what did X represent? X represented our height of our palm tree, right? So a palm tree, V feet, will require how much water? 50 gallons of water. And then down here, D, palm trees are an average Z feet high, and a tree of average height requires K gallons of water. Represent this fact in terms of P and -1. Okay, so we went, our original was P feet. So P of X, which that's going to be Z, is equal to amount of water, K. The inverse would be P of K is equal to Z. Okay, we are going to skip all of E, because I think that is unnecessary, and we're going to jump to number 7. at the bottom of that page. So now we're going to be given a table, and we're going to be given function notation, some of them compositions like you see there in C and D. So we have function f on the table on the left, function g on the table on the right. When it comes to these problems, what I like to do just to organize things, I'm a visual person, so I kind of need to see it and less stuff happening in my head, is I like to do a table of the inverses below or to the side where we have space. So if I did the inverse of this function, then my x's will all become the y's of the original. So 2, -1, -3, and -4. And then my outputs of the inverse function would be all the x's. So -1, 0, 3, 5. And then I can do the same thing for g. So x, and then outputs of the inverse would just be all of the x's of the domain. So flipping the g function would get us -6, -1, -3, 1, 4, -1, 6, 8. So now I have my regular f, I have my regular g, I have my inverse f, I have my inverse g. So now we can evaluate a through d. So f inverse of -4 would be down here at 5. G inverse of 6 would be down here at 8. Equals 8. Composition, work inside first. So g of 1 is up here, gets us -3. So then we're going to do f inverse of -3. So down here at -3, the f inverse is +1. F of 0 is -1. G inverse of -1 is, where are we at? Oh, G inverse? Oh, sorry again. I see what I did wrong. I was like, why don't I have a -1 in here? I forgot to invert my -1, 4. There we go. So -1 gets us an output of 4. Okay, so now we're going to get into how we can find inverses of rational functions to finish up our notes. So we know how to find inverses of linear, cubic, square root functions, all of those, but how do we do it when it's a rational function? Because now we have, notice, 2 x's, an x in our numerator and an x in our denominator. That's what makes it a rational function. So let's go ahead and find the inverse of function f. I'm going to make my f of x, x. I'm going to make my y, or xy, so 2y plus 3 over y plus 2. Now I need to solve this equation for y. So I'm going to clear out the denominator first by multiplying by y plus 2. What I do to the right, or the right I need to do to the left. I'm going to distribute that x. So now I have xy plus 2x is equal to 2y plus 3. Now I have 4 terms, 2 of which have a y involved, 2 of which do not have a y involved. So I want to move all my terms that have y's to one side and all my terms that have x's to another side. Because this 2x is positive, I'm going to put all my non-y terms to the left. I'm going to move this y term over. I'm going to subtract my 3 over to both sides. So what do we end up getting? We end up getting 2x minus 3 is equal to 2y minus x. I can factor out my y from both of those terms, which gets me 2 minus x inside. I'm going to end up dividing, running out of space here, divided by 2 minus x. So I get y is equal to 2x minus 3 all over 2 minus x. You're more than welcome to leave your answer like that. If you don't like the 2 minus x, we can, so again, we can do that. Just make your y in inverse notation, so f inverse of x. We could factor out a negative from that denominator, which would make my x positive and my 2 negative, and then just move this negative out in front. So 2x minus 3 over x minus 2 with a negative out in front would get you the same answer. So either of those are acceptable. If you would have shifted your y terms to the left and all your non-y terms to the right, then you would have gotten probably negative 2x plus 3 all over x minus 2 for your final answer, which is equivalent form. But again, it's best practice to put that negative in front, and when you do that, then that's going to make that 2 become a positive, and it's going to make that 3 become a negative. Because then when you distribute that back over, it would get you back to your original problem. Okay? All right. So, anyways, just leave it up there at that first one. What would be the domain on our inverse function? Well, you should be able to see that it's everything but 2, right? So negative infinity to 2, jump it to infinity, which makes sense because the domain of f of x is restricted at negative 2, right? So go back up to our original, x plus 2, x can't equal negative 2. So our domain was negative infinity to negative 2, jump negative 2 to infinity. And our range of our original function should be the domain of the function, so everything but 2, which should make sense because if you go back to the original function, we get range restrictions, let's move this for a second, from our horizontal asymptotes. And what's my horizontal asymptote? Well, my degrees are the same, so the leading coefficient ratio, which would be 2. Right, so I would have a horizontal asymptote at y equals 2, which means my range would be jumping over it. Okay, example number 9. If a function is not one-to-one, then its inverse does not exist. However, if an appropriate restriction on the domain is made, then we can find an inverse that would also then be a function. So we said earlier that a quadratic graph, right, is a function, but if I do the inverse of it, it no longer is a function. It doesn't pass the horizontal line test. So if I can restrict my quadratic to just one side of my function, then the inverse would also be a function itself. So that's what's happening here. You are never going to have to make the restriction yourself. You would probably be given the restriction in the problem. So notice here, they're giving us the quadratic and they're restricting it to just the positive values. So if I wanted to find the inverse, make my y an x, my x a y, solve for y, subtract your 2 over negative y squared, make everything opposite in size to make my y positive, square root. So we got, f inverse of x is equal to the square root of, let's rewrite this as 2 minus x. Now we have to think about the domain, right? So what's our restriction on the domain? Well, we know in absolute or in square root functions, 2 minus x needs to be greater than or equal to 0, which means, just move that over, 2 has to be greater than or equal to x, which is the same as x is less than or equal to 2. So what does that look like in integral to notation? Negative infinity to 2. All right, so let's graph both of these. So we're graphing our first function, which is just a regular quadratic, shifted up 2, flipped upside down, but we only want to do the positives. When I plug in 2, we get 4. 2 minus 4 is negative 2. So we have this graph right here. Graphing the inverse. At 0, 2 becomes 2, 0. 1, 1 stays 1, 1. 2, negative 2 becomes negative 2, positive 2. So we have this happening for our function like that. All right, last example. Suppose f of x and g of x are one-to-one functions. If f of 3 equals 5 and g of 5 equals negative 2, can you determine whether f and g are inverses of each other? So if f of 3 is equal to 5 and the inverse of 5 should equal 3, right? So if we want to know if G is the inverse, then G of 5 should equal 3, which it does not. So it is not an inverse. All right, that concludes your notes.